Hello children, welcome back. Today we have chapter waves, last chapter of the first year topics. For quick revision, today we begin with what are waves? Waves are the modes of transfer of energy from one place to other place without the actual transfer of the medium or without the actual transfer of the particles of the medium. But the energy propagates. Particle of the medium only vibrates. Energy propagates. So there is no translation of particles, no net translation of particles. That's a definition. Waves are modes of transfer of energy. That's all. Generally classified into two: mechanical and non-mechanical. Non-mechanical waves are electromagnetic waves. Electromagnetic waves are non-mechanical and they do not need any material medium, but mechanical waves, they need a material medium. We, for first year topics, learn only about mechanical waves. Mechanical waves need medium. There should be few of the properties of the medium that should be defined for that medium, and one of that properties is elasticity. Medium should possess elasticity, then only the particles of the medium would oscillate and it can come back to the previous state. Particles of the medium undergoes to and fro motion. The second property is inertial property, inertia. The particle, when displaced, it tries to come back to the mean position. At mean position, it cannot come to a sudden stop. Instead, due to inertia, it should overshoot. Then it should continue oscillating. So, restoring force and inertia. Medium should have elastic properties. Then only it will show all this. There should be a restoring force acting on the particles for oscillation. The same condition is needed here. That restoring force acting on the particle should be proportional to the displacement, and the phase angle between restoring force and displacement should be 180 degree. All these conditions are satisfied. If the particles of the medium undergoing simple harmonic oscillations, such a wave is called a harmonic wave. The mechanical harmonic waves can be classified into two broad categories, depending upon the orientation of the vibration of particles. The first one is transverse. As the name says, transverse vibrations, particles of the medium vibrates at right angles to the wave. Second one is longitudinal waves. Longitudinal waves, particles of the medium vibrate parallel to the direction of propagation of the wave. So there are two velocities associated. One is the particle velocity, other is the wave velocity. Wave velocity is a constant for a given medium. But when the medium changes, velocity of the wave changes. But particle velocity is not a constant. It continuously varies. Particle velocity has its maximum value at the mean position and is zero at the extreme. So particle vibrates, wave translates. Wave has a constant velocity in one medium. But when medium changes, velocity changes. When velocity changes, wavelength also changes. But when medium changes, frequency does not change. When these longitudinal waves, mechanical waves, move from air to liquid or any gas to liquid, the speed slightly increases. Then liquid to solid, again speed increases. The change in speed all depends on the elastic and inertial properties of those media. But frequency does not change when medium changes. Frequency does not change when medium changes. Now, two types of waves we have already discussed. That is called longitudinal as well as transverse waves. Transverse waves have two main parts of the medium that are called crust and troughs. Crust is the region of maximum displacement in one direction and trough is in the other direction. The length of one crust and trough is called wavelength. Distance between two consecutive particles which are in same state of vibration also is called one wavelength. The distance between two particles of the medium, that is an integral multiple of wavelength. There is a constant relationship between this wavelength and phase difference and path difference. That relationship is looking like this. 2 pi by lambda is a proportionality constant. The phase angle between any two particles in which a traveling wave is propagating is found to be equal to 2 pi by lambda times the path difference. So this proportion is very important. So that phi equal to k times delta, where k is the angular wave number or propagation factor. So phi by delta can be written as k. The proportionality constant phi by delta is 2 pi by lambda. This phi by delta can be written as 2 pi by lambda. Lambda can be written as velocity divided by frequency. Lambda equal to v by f, where f is the frequency. Where this 2 pi f may be written as omega, angular frequency of the wave, divided by velocity. That is k is equal to omega by v, or omega equal to vk, or v equal to omega by k, where this v is called the wave velocity or phase velocity. So these type of discussions are important. When a traveling wave is advancing through a medium, no two neighboring particles are in phase. There will be a slight phase difference. You can find out that phase difference between two neighboring particles by using this relation theta is equal to omega t. If t is the response time or time interval between the disturbance passing through two neighboring particles, and omega is the angular frequency, then multiply omega t will be the phase angle between the two. So all these things are important. When a traveling wave is propagating through a medium, two neighboring particles will be out of phase. That phase angle is never zero. Then only that wave can advance. In a homogeneous medium, it travels with constant speed. Okay. Now, we move on to this particular topic, transverse waves in a stretched string. Transverse waves, we so far discussed transverse waves in crusts and troughs. One crust plus one trough is called one wave. Length of one wave is the wavelength. Wavelength is the distance traveled by the wave when each of those particles in the medium makes one vibration, or it is defined as the shortest distance between any two particles of the medium which are in same phase. There are many more particles which are in same phase. All those particles will be separated by an integral multiple of this minimum wavelength. That is wavelength. Now, transverse waves in a stretched string. Transverse waves in a stretched string. This topic is very important. Transverse waves in a stretched string. When a transverse wave is propagated in a stretched string, its velocity is measured as root of t by mu, where mu is the linear mass or linear density. If m is the mass of that stretched string and L is its length, velocity can be, wave velocity or phase velocity can be expressed as root of t divided by m by L. This can also be expressed as t by a rho, where t by a is the tensile stress developed in that stretched string. So that can also be written as the tensile stress divided by density. All these expressions are to be noted. That is root of T by area of cross section of the wire A may be expressed as pi r square. So T by pi r square. So on what factors V depends? V directly proportional to root T. If tension is doubled, velocity becomes root 2 times. Velocity proportional to 1 by r. If radius is doubled, velocity becomes half. Again, V proportional to 1 by square root of rho. If density is doubled, velocity becomes 1 by root 2 times. So V equal to root T by mu, V equal to root T by a rho, V equal to root stress by density, V proportional to 1 by r, V proportional to root T, V equal to root of T by pi r square rho. All these are very important equations. Okay, based on which you can answer the questions so easily. This type of comparison question, V1 by V2 equal to R2 by R1, VR graph is a rectangular hyperbola, V proportional to T, so T proportional to V square, T proportional to V square. So TV graph is a parabola, TV graph is a parabola, V equal to root of T by pi r square rho. Stretched string, the wave is called transverse progressive wave or transverse traveling wave. So this equation is important. And let us apply this once. If you have a stretched wire or a loaded wire, a wire is suspended like this. Suspended freely. The mass of the wire is m, length of the wire is L. What is the velocity of a wave which is originated at the bottom and is traveling upward when it reaches a point P, which is at a distance x from the free end? It's a string hanging whose mass is m and length is L. A wave is originated from the free end and it travels in the upward direction. What is its velocity when it reaches a point P from distant x from the free end? For that we can use this formula, V equal to root of T by mu, where T is the tension at the point P. Tension at the point P is the weight below the point P. Weight below the point P will be mass below the point P into G. Mass below the point P is mass per unit length into length below the point P. Mass below the point P equal to mass per unit length into length below the point P. So mu x into G. Okay, divided by. So root of tension. Tension is mu x G. Tension at the point P is mu x G divided by mu. T by mu gets cancelled. So you get V as root of xg. So velocity is root of xg. As the wave goes upward, x increases, so velocity increases. When velocity increases, wavelength increases. But still, frequency does not change. So as the pulse is moving upward, its velocity and wavelength both increases, but its frequency does not change. Okay, now longitudinal waves. Longitudinal waves, there are compressions and rarefactions. Compression means region of high pressure. Rarefaction means region of low pressure. Compressions and rarefactions. In compression, density and pressure are maximum, but in rarefaction, density and pressure are minimum. So wave advances in compressions and rarefaction. Distance between two neighboring or consecutive compressions is called a wavelength, or distance of one compression plus one rarefaction is also wavelength. That is longitudinal waves. Longitudinal waves when travel in a medium. The formula for velocity. Longitudinal traveling wave. When passes through a medium, its velocity is measured as square root of bulk modulus divided by density. As per Newton's formula. When longitudinal wave passes through air, or sound passes, sound is longitudinal in air. So when sound passes through air, Newton assumed that that process is an isothermal one. That is, air undergoes isothermal changes when sound passes through it. Then that bulk modulus is isothermal bulk modulus or isothermal elasticity, which is shown to be equal to the initial pressure. So that velocity equal to root of P by rho. But we have learned in kinetic theory, P by rho has to be RT by M0, where M0 is the molar mass. So this should have been the formula for velocity, but it is incorrect. There is many discrepancies, lots of discrepancies in comparing with the practical results. For that reason, Laplace formulated a new one called Laplace formula. As per Laplace formula, the bulk modulus is adiabatic one. Adiabatic bulk modulus is equal to gamma times initial pressure, where gamma is Cp by Cv, ratio of specific heats. Then velocity becomes root of gamma P by rho or root of gamma RT divided by M0. So you can use this second formula, that's very important. So velocity proportional to square root of temperature, velocity proportional to square root of gamma, velocity proportional to 1 by square root of M0. We know as P by rho is a constant. Variation of pressure at constant temperature is not affected because P by rho is a constant at a constant temperature, because P by rho is equal to RT by M0. At constant temperature, P by rho is a constant. At constant temperature, P by rho is a constant. So that's longitudinal traveling wave. So sound when travels through air, you can use formula velocity equal to root of gamma RT divided by M0. We have learned RMS velocity formula. VRMS velocity of gas molecules root of 3RT by M0. But speed of sound is equal to root of gamma RT divided by M0. This comparison is very important. Don't confuse between each of these. Okay, for every unit degree rise in temperature of air, speed of sound increases by 0.6 meter per second, for which every 10 degree Celsius rise of temperature, speed of sound in air increases by 6 meter per second. That is to be noted. Okay. So we have learned longitudinal as well as transverse waves. With each cases we have learned examples. Okay. Now, reflection of progressive waves. Reflection of progressive waves is the next important topic. Reflection. Two cases are to be learned. Reflection at a fixed or rigid boundary. Reflection at a rigid boundary or fixed boundary. When a traveling wave undergoes a reflection at a rigid boundary, there causes a crust to be reflected as a trough or trough to be reflected as a crust. Similarly, compression to be reflected as a rarefaction, rarefaction to be reflected as a compression. So there is a phase angle of pi radian or 180 degree, due to which when a compression is reflected as a rarefaction, compression has an amplitude plus a, rarefaction has an amplitude minus a. On adding algebraically, plus a plus minus a becomes 0 naturally. So the region of no displacement is seen, which is called a node. So at a rigid boundary, due to reflection, nodes are seen. Nodes are those regions whose resultant displacement is 0. So amplitude of that wave at nodes would be 0. That is why there is no energy. That particles are stationary. At nodes, particles are seen to be stationary. Second one is reflection at open boundary or free boundary. In free boundary, the phase angle observed as 0, no phase angle. So that is called an antinode. Antinode is the region of maximum displacement. Node is the region of zero displacement. So progressive waves or traveling waves, reflection of progressive waves, reflection at rigid boundary and free boundary no phase angle, rigid boundary there is a phase angle of pi radian. This much to be by heart. Okay, now standing waves. Standing waves, as the name says, are standing waves because they are not carrying any energy from one place to other place. So energy is confined within certain regions. Energy is not being propagated because of the presence of nodes frequently in between, and that nodal points, amplitude or energy of vibrating particles would be zero. Particles does not vibrate at nodes. When a traveling wave is propagating in one direction, is superimposed by another one in the opposite direction, having same amplitude, same velocity, same frequency, which produces the resulting wave as a standing wave. If one of the waves y1 is equal to a sine kx minus omega t, representing a progressive wave. It's a progressive wave. Progressive wave propagating in positive direction of x-axis. This minus sign will tell you the direction of the propagation has to be positive x-axis. Here is the coefficient of k. Angular wave number is x. So positive x-axis. This sign is negative. So wave is propagating in positive x-axis. Omega is the angular frequency, and I have earlier written omega by k is the wave velocity. So this is general formula. A is the amplitude of the wave. This is general formula for a traveling wave. You have another traveling wave y2 having same amplitude, same angular wave number, same angular frequency, but they are traveling in opposite direction. These two, when added together by using superposition principle, by using suitable trigonometry, you can use identities, you can use the addition. You get 2a sine kx cos omega t. This is a pattern. Here it can be seen that this amplitude term, which is a position dependent term, is not a constant variable. So amplitude of standing wave can be written as amplitude of standing wave. A dash is equal to 2a sine kx. So what is the condition for a node? At node, we know amplitude should be 0. That means minimum. For which sine kx is equal to plus or minus 1, or kx is equal to plus or minus 1. That's why kx is equal to n pi. Then x is equal to n pi divided by k. K is 2 pi by lambda. So x is equal to pi gets cancelled, n lambda by 2. So at what all values of x nodes are frequently repeated? Put n equal to 0. Put n equal to 1. So 0, half lambda, then 3 lambda by 2, then next one, 1 lambda by 2, 2 lambda by 2 is lambda, 3 lambda by 2, 4 lambda by 2 is 2 lambda, so and so. Each of those nodes are separated by a distance of lambda minus lambda by 2, or 3 lambda by 4 minus lambda, or 2 lambda minus 3 lambda by 4, all lambda by 2. So distance between neighboring nodes is equal to half the wavelength. That's the condition for a node. Now condition for antinode. Condition for antinode. That is 2a sine kx is equal to 2a sine kx is equal to maximum. Then only that is antinode. For node it was 2a sine kx was 0, for which sine kx was 0. For condition for sine kx to be 0, that is kx should be equal to n pi. Now, but here it should be maximum, for which sine kx is equal to Antinode should have be maximum. So what is Kx? Kx is equal to n plus 1 by 2. That is x is equal to 2n plus 1 pi by 2k. K is 2 pi by lambda. Pi gets cancelled. So x is equal to 2n plus 1 lambda divided by 4. Putting values. X is equal to lambda by 4. X is equal to 3 lambda by 4. Then 5 lambda by 4, etc. That's the condition for antinode. So antinodes are separated, also separated by lambda by 2. So not separated by lambda by 2. Antinodes also separated by lambda by 2. Okay, neighboring nodes and neighboring antinodes are separated by distance half the wavelength. That's antinode. So what are nodes and antinodes? Standing waves are composed of nodes and antinodes. Antinodes are regions of maximum displacement and nodes are regions of zero displacement. Okay. The particles of the medium on either side of a node are 180-degree out of phase. Particles between any two neighboring nodes are 0-degree out of phase. When a standing wave is contained in a medium, the medium particles will have only two distinct phase angles, either 0 or 180. We can easily understand by using standing waves in stretched strings. Standing waves in stretched strings. Let us choose one example. I am drawing a stretched string which is stretched between two rigid supports like this. I am plucking the string at the middle. Exactly at the middle you pluck the string. Then the pattern of vibration of the mechanical vibration, transverse vibration of the string can be seen like this. And the region of node displacement is node and maximum displacement in antinode. The first node may be at x equal to 0, let that be the origin. Now x equal to lambda by 2 is the first node, which is L, is the length of the string, which is equal to lambda by 2 minus 0. So L is equal to lambda by 2, so lambda equal to 2L. Now the string vibrates in only one segment, that is called first harmonic. First harmonic or fundamental frequency. First harmonic or fundamental frequency is given by V divided by lambda, but lambda equal to 2L. That is fundamental frequency. For the next harmonic to be heard, you stretch the same string without any changes in the geometry. Take the same string, pluck at 1/4. Pluck at 1/4. If you pluck at 1/4, you get a pattern of mechanical vibration like this, where here x equal to 0 and here x equal to lambda. That's why L is equal to lambda. Okay, then that frequency can be written as V by lambda is L. So V by L, multiply and divide by 2, you can see that this is 2 times fundamental frequency, so called second harmonic. So second harmonic nu2 equal to 2 times V by 2L. First harmonic is V by 2L, second harmonic is 2 times V by 2L, where V is the velocity of transverse waves in a stretched string. V, earlier we have the formula root of T by V. This can be used. In the second case, there are 3 nodes and 2 antinodes. That is called second harmonic. Second harmonic is also called first overtone. So first overtone is the second harmonic. Now third harmonic is going to be 3V by 2L. Fourth harmonic 4V by 2L. That is, each of these frequencies are certain characteristic values. You cannot notice any other frequencies in between. So frequencies get repeated in steps. Okay, integer multiples of V by 2L. That's the thing. But this is possible only without changing the geometry of the string. Same string, same length, same mass, same radius, same tension, everything same. Okay, you can pluck at the middle to hear fundamental. If you pluck at 1/4, you get double the frequency. The frequency you hear is double the frequency of the same. That is, standing waves in stretched string. You can see the node at the middle here. Any particle to the left of the node is vibrating, say, downward at an instant. At the same instant of time, any particle to the right of the node is vibrating in the upward direction. So the phase angle between these two particles is 180 degree. But any two particles you see in between two neighboring nodes, they will be vibrating in phase. Any two particles falling between two neighboring nodes will be vibrating in same phase. That means here it vibrates in two segments. The left segment when goes down, right segment goes up. So it will vibrate like this. So any number of segments are vibrating. Neighboring segments are vibrating 180 degree out of phase and alternate segments are vibrating in phase. If the number of closed loops seen is 3, that is third harmonic. If number of closed loops noticed is, segments noticed is 10, that is 10th harmonic. This is the principle. Okay. Is it clear? Then each of those frequencies can be first harmonic, second harmonic, third harmonic, all bear the ratio frequencies 1, 2, 3, 4, 5, 1 is to 2 is to 3 is to 4 is to 5, like that. Okay. Now, standing waves in organ pipes. Standing waves in organ pipes. Organ pipes are of two categories. First one is closed organ pipe. The organ pipe whose one end is closed and the other end is open is called a closed organ pipe. If you choose a closed organ pipe like this, closed organ pipe is of length L. Length of the closed organ pipe is L. You excite a tuning fork at the open mouth, then the vibrations, longitudinal vibrations reach the bottom where there is a fixed and rigid end. There it reflects and forms a node. And the open mouth, as the density is less, at the boundary is a rarer boundary, it gets an antinode. So the first possibility of the diagram is this. Here x is equal to 0. The next antinode is x is equal to lambda by 4. So you will get the L lambda relation, L equal to lambda by 4. Then L by lambda is 1 by 4. That means lambda is equal to 4L. So fundamental frequency is V by lambda. Lambda is 4L. Okay. The next harmonic, for getting the next harmonic, you should not alter the geometry. Keeping the same geometry fixed. Okay, you use another tuning fork. You increase the frequency of the tuning fork used gradually. Say you have a continuous, large number of continuously increasing frequencies of forks. And you successively excite at the open mouth. You can listen to a louder sound when the pattern is of this shape. And the vibrations are in two nodes and two antinodes. Then the distance here x is equal to 0, here x equal to lambda by 2 at middle, not middle, here it is x is equal to 3 lambda by 4. So lambda by 2 plus lambda by 4. And that is L. That is L is equal to 3 lambda by 4. So lambda equal to 4L by 3. Then that frequency nu is equal to V by lambda. Lambda is 4L by 3. So that is thrice fundamental frequency. So it should be nu 3. Nu 3 equal to 3 nu 1. That is why the next higher harmonics heard will be only 5 times nu 1. So 1 is to 3 is to 5 is to 7 will be the successive harmonics. So harmonics ratio 1, 3, 5, 7. You take the difference of any two neighboring. 9 minus 7 is 2. 7 minus 5 is 2. 5 minus 3 is 2. 3 minus 1 is 2. Okay. Then 2 is the common difference. You take half that will be 1 and that is fundamental. That will be like this for any closed organ pipes. So closed organ pipe you can excite only odd harmonic. And third harmonic is first overtone. Third harmonic is first overtone. Third harmonic is first overtone. And this happens to be the first harmonic. First harmonic is V by 4L. Third harmonic is first overtone. Nu3 equal to 3 nu1. Nu5 equal to 5 nu1. Nu7 equal to 7 nu1. So 1 is to 3 is to 5 is to 7, etc. Okay, that's very important. So closed organ pipe as well as next one is open organ pipe. Second type, open organ pipe. In open organ pipe, the pipe is open from both ends. Pipe is open from both ends whose length is L. Then the first possibility is to have two antinodes at each ends with one node in between. So L is equal to what? Here, this distance of separation will be lambda by 2. So L equal to lambda by 2. Lambda equal to 2L. Nu equal to V by lambda. Lambda is 2L. So V by 2L is the first harmonic. So second harmonic is present, that is 2V by 2L successively. You can follow this. Nu3 equal to 3V by 2L, so and so. But number of nodes is equal to the harmonic. If second harmonic, 2 nodes and 3 antinodes would be there, and number of antinodes would be greater by 1. So the relations between number of nodes and antinodes in each of these cases can be distinctly learned. That's open organ pipe. Open organ pipe fundamental frequency V by 2L, but closed organ pipe fundamental frequency is V by 4L. If you have two organ pipes of same lengths, the ratio of fundamental frequencies of closed and open is 1:2. Open and closed is 2:1. That is frequency of fundamental frequency of open organ pipe is exactly double the fundamental frequency of closed organ pipe. Okay, let us do one problem from this. If you have a closed organ pipe like this, suppose you have a closed organ pipe having fundamental frequency 100 Hertz, whose length is equal to 30 centimeter. The fundamental frequency 100 Hertz. Now you cut it into two pieces. Cut into two pieces. The smaller piece is of 10 centimeter and the longer piece is of 20 centimeter. Okay, what is the ratio of frequencies of these two pipes, fundamental frequencies? Here the fundamental frequency can be noticed like this. Here it can be noticed like this. This is closed, still closed. This one was totally closed. This part becomes closed and this part becomes open. Okay, let us apply whatever we have learned here. Now, what is the fundamental frequency of this? This one is of length 20 centimeter and this is of length 10 centimeter. This much data is to be given. See here, this is a closed pipe with fundamental frequency 100. This is a closed pipe. So closed pipe fundamental frequency should have been same if length was same. But its length is how much? 2/3. Its length is 330. Here only 1020. So length has become 2/3. Frequency proportional to 1 by L. That is why length has become 2/3. Frequency becomes 3 by 2 times. So 100 into 3 by 2, that is 150 Hertz. Now going to this pipe. Here fundamental is 100 but it is closed. Here fundamental should be double that of closed. So that should be 200. If that was of same length, still length is different. What has become length? 30 was the original length. Length of this pipe is only 10. Length has become 1/3. When length becomes 1/3, frequency becomes thrice. So 200 into 3, that becomes 600 Hertz. So what is the ratio of those frequencies of closed and that open? 150 is to 600, that is 1:4. This type of questions can be applied. This may be the possible way to have an increased speed. So open organ pipe, closed organ pipe, fundamental frequencies, overtones, all these are very, very important. Students, hope that it is useful to you. Next topic is production of beats. Beats are another applications of superposition. Beats are formed when two slightly different frequencies superimpose irrespective of the direction in which they are superimposing. But they should be of same speed, they should be of same amplitude or nearly equal amplitude, but frequencies are never same, slightly different. If frequencies are largely different, also beats are formed but is not audible. Audible beats are heard mostly when frequency difference is not much larger than 10 hertz. It should be 10 hertz or less than 10 hertz or close to 10 hertz. Then only that frequencies of beats are audible. Beats are formed when two slightly different frequencies superimpose, and the beats are the variations in intensity of sound when these two slightly different frequencies superimpose. So beats are formed when two slightly different frequencies superimpose. Let y is equal to a cos omega 1t. Next, displacement of the second wave when passes through the same medium, a cos omega 2t. Superposition principle, y equal to y1 plus y2, using any trigonometrical identities corresponding, you can solve this to a cos omega 1 minus omega 2 by 2 t cos omega 1 plus omega 2 by 2 t. Here 2a cos omega 1 minus omega 2 by 2 t represents the amplitude term of the beat. So you can see amplitude varies with the time. 2a represents the maximum amplitude of the beat. Beats are, listen, beats are variations in intensity of sound. The maximum of intensity heard is called waxing, minimum is called waning. One beat means one waxing plus one waning. Two beats means two waxing plus two waning. Okay, here you can see few more terms here. Two independent frequencies are omega 1 and omega 2, they are slightly different. You get one frequency which is omega 1 plus omega 2 by 2. That is the frequency that really listen to. Even when you excite these two frequencies together, you only listen to one frequency which is the arithmetic mean of these two. Okay, that is the frequency heard. But in addition to that, you listen to variation in intensity of sound at a frequency omega 1 minus omega 2. That is called beat frequency, and beat amplitude varies at a frequency omega 1 minus omega 2 by 2. This is the beat amplitude. So amplitude varies at what frequency? Omega 1 minus omega 2 by 2. Intensity varies at double the frequency of variation of amplitude. Intensity varies at double the frequency of variation of amplitude, because intensity proportional to square of amplitude. Okay, if frequency of cos theta is x, frequency of cos square theta is 2x. That's why cos square theta cannot have negative values. That's why intensity has variation frequency omega 1 minus omega 2, which is called beat frequency. So beat frequency, new beat frequency, it's very important. Beat frequency, new beat is equal to nu 1 minus nu 2 in the units of hertz. And angular frequency omega beat equal to omega 1 minus omega 2, that is expressed in radian per second. That's very important. Then beat period, 1 by beat period is equal to 1 by T1 minus 1 by T2. All these things are to be very well noted. That's beat frequency. One example. If nu1 is equal to 256 hertz and nu2 equal to 258 hertz, how many beats are heard per second? That nu1 minus nu2 equal to 258 minus 256, bigger minus smaller, that is 2 hertz. That means in 1 second you will listen to 2 waxings and 2 wanings. That is beat frequency of 2 hertz. Okay, what frequency you have listened to? Arithmetic mean, that is 257 hertz is the frequency of the sound you heard. But periodic variation in intensity of sound you have heard is 2 hertz. What is the variation of beat amplitude? That is nu1 minus nu2 by 2. That is 1 hertz. Amplitude varies at 1 hertz, but intensity varies at 2 hertz. Frequency, that is called beat frequency. So beats are the variation in intensity of sound when slightly different frequencies superimposed together. Okay, beats are heard when two slightly different frequencies superimpose. Okay. Next topic is, the last topic of the chapter is Doppler effect. Doppler effect. Doppler effect in this phenomenon, whenever there is a relative motion between a source of sound and listener, the frequency heard by the listener, frequency of the original frequency of the sound is not heard by the listener. Whenever there is a relative motion between source and listener, that frequency may be more or less, and that heard frequency will be a constant one if the relative velocity is a constant. But if the distance between source and listener does not change, that means if there is no relative velocity between source and listener, then there is no such effect. Suppose you have a source. You have a source of sound. Suppose you have a source of sound here. Source of sound. Source is producing a sound in all directions. Okay, we have a listener also. Listener is here. At same level, the listener receives the sound. Listener receives that sound. The frequency of the source is F. True frequency of the source is F. The wavelength of the wave received by the listener is lambda. What is the wavelength of the listener? Listener is at rest. If the listener is at rest, source is also at rest. What is the wavelength received? If v is the velocity of sound, then the wavelength received lambda is equal to v divided by f. So lambda is the wavelength received by the listener when listener and source both at rest. Okay. Now assume that the source is moving away. Source is moving away from the listener with a velocity. Assume that the source is moving away from the listener. Source is moving away from the listener with a velocity VL. Then, as the source is moving away, the listener listens to a reduced frequency and increased wavelength. Now, what is that wavelength listened? The new wavelength lambda dash is equal to, frequency has not changed, but wavelength has become. What is the new wavelength? That is V plus VL. Because you have to see the relative velocity of the sound with respect to the listener. With respect to the listener, source is not source, should be Vs, right? Vs, and it should be Vs, right? It's not VL. Listener is at rest. Source only is moving. Now, relative velocity of the sound with respect to the source, with respect to source velocity of sound, you can see that it should be V plus Vs. So lambda dash is equal to V plus Vs divided by F. When the source is moving away. At the same time, if next third case, the listener is also moving in the same direction with unequal speeds. VL is not equal to Vs. Then what is the frequency heard by the listener? The frequency heard by the listener is equal to frequency heard, frequency equal to velocity. What is the relative velocity of the sound with respect to listener? That should be relative velocity of sound with respect to listener. That is also V plus VL. because sound and velocity of listener are in opposite direction. Relative velocity is v plus vl divided by wavelength lambda dash. That is why f dash is equal to v plus vl divided by lambda dash. Lambda dash is v plus vs by f. That is, f dash is the heard frequency, f is the original, v is the speed of sound, vl is listener velocity, vs is the source velocity. This formula only should be used when source and listener are moving in same direction with dissimilar speeds along same straight line, one-dimensional Doppler effect. Okay, from this you can develop what is the frequency if listener is at rest, source is moving away, listener at rest, source is approaching. Source and listener are in motion with the source chasing the listener. When both are moving in same direction but source chases listener, then this formula, if you try to deliver like this, you get V minus VL by V minus Vs, which is in your textbook in CRT. Okay. Now Doppler effect in reflected sound. Doppler effect in reflected sound. Whenever Doppler effect in sound is learned, you should not avoid this one. It's very important. While Doppler effect is happening, if source is moving, wavelength changes. If source is not moving, wavelength does not change. But frequency changes. It's not the real change, only apparent change. If the distance between source and listener does not change, there is no such effect. If the source or listener having relative velocity perpendicular to the line joining source and listener, suppose source is moving at right angle to the line joining source and listener, then there is no effect. That means the relative velocity should have a component either along towards source or along away from the source. Then only there is a Doppler effect. In Doppler effect, it is the apparent change in the frequency, not the change in intensity. When a source of sound approaches you, you may have noticed the increasing sound, that is increasing intensity. Intensity of a point source varies inversely with the square of distance. But that is not the Doppler effect. Due to Doppler effect, if relative velocity is a constant, you listen to a constant higher frequency when approaches, constant lower frequency when moves away. Okay. Now reflected sound. Suppose the source of sound producing source produces a sound, and here is the source. That source may be a car, maybe a car, it may be a car, it may be a car. Car is moving with the velocity of the source towards a cliff, maybe a cliff. Okay. Now sound goes towards that direction. The driver of the car is sitting here. Driver is happening to be the listener. Listener is also moving in the same direction. So listener and source are having same velocity. The sound undergoes a bouncing back here. Sound comes back. In such cases, you can imagine that this cliff has to be a plane mirror. Cliff has to be a plane mirror. So that the reflected image of the car approaching it like this. Then you can develop the equation. That means source is approaching, then source is approaching, listener is also approaching the cliff. So imagine that the source itself is here now. Source is approaching from that side, listener is from here. So these two are moving towards each other. So this should be the source. Source is the car. so producing the sound. Let that car be coming from ahead at same distance. Like this. Listener is this one. So which formula can be used? F dash is the frequency heard by the listener is here. Listener is here. F dash. F is the frequency of the source. F is the frequency of the source. So F dash is equal to F into, you can use source and listener are approaching. Source is this one, listener is this one. So V plus VL divided by V minus Vs. While considering velocity of sound and the source, velocity of sound and source, they are in same direction. Then minus. Velocity of sound and listener. Velocity of sound is coming from this reflected sound. Doppler effect for reflected sound. Listener is approaching towards right, so that sign should be plus. In such cases, maximum Doppler effect heard. Okay. Now this driver can listen two frequencies. One original frequency, the other one frequency due to the reflected effect. So that frequency differences, if not much larger, he may listen to number of beats also. Most of the frequent papers we used to see such questions. So what is delta F heard by the listener? Original frequency is F, heard frequency is F dash. So F dash minus F, you can subtract these two. You can try to get that answer. So delta F is equal to F dash minus F. F dash is F into V plus VL divided by V minus Vs, then minus 1 I have taken, F as common factor. That equals F into, taking LCM, V minus Vs, numerator, V plus VL minus V plus Vs. So V gets cancelled. So delta F is equal to VL and Vs are equal. We have taken VL and Vs are equal because car and listener, which is the driver, all are having same velocity. So VL and Vx we can write x. So 2 V minus V0 2x F divided by V minus Vs. Like this, you can make trial and error and make different situations, keeping listener at rest, source in motion. Like this, you can try to practice. Okay, any doubts you can ask. Now, similar questions have been seen in mains as well as advanced papers recently. Lots of questions have been seen. Now, you can practice all these things. Anyway, let me repeat what is Doppler effect once again. Doppler effect is the phenomenon by which there is an apparent change in frequency heard by the listener whenever there is a relative motion between source and the listener. Whenever source moves, there is a change in wavelength. Okay, if source is at rest, listener is moving. That is why the Doppler effect is listened. Then there is no change in wavelength. When source is approaching the listener, stationary listener, wavelength reduced, frequency increased. Doppler effect in sound is highly asymmetric because a small change in any one of these parameters, even direction, makes a lots of differences. But in light, Doppler effect is symmetric. Light does not need any material medium. So the presence of medium or velocity of the medium, that doesn't matter for light. So Doppler effect in light is symmetric. Doppler effect in light has changes in wavelengths also measured with change in frequency. Okay, both comes together irrespective of whether source or observer are rest or moving. So in Doppler effect, there is an apparent change in frequency. Okay, in addition to that, there is a variation of intensity that is not measured as Doppler effect. There should be a slight change in the frequencies to produce beats. So beats, Doppler effect, these connected questions are very important. Also standing waves, organ pipes, stretched string standing waves, then progressive waves. This chapter is that much. Okay, hope that you are clear with this. We will be meeting with second year topics. Thank you.